Space is vast, so vast that traveling between stars could take millions of years. But what if there was a shortcut? A cosmic tunnel that could take you across the galaxy in an instant? This isn't just science fiction, it's a concept deeply rooted in Einstein's theory of relativity. They're called wormholes. But do they actually exist? Could we ever travel through them? And if so, what lies on the other side? Imagine you're an astronaut standing on one side of the universe and you need to reach the other side. Even if you traveled at the speed of light, the journey could take thousands, even millions of years. But what if there were a shortcut? A tunnel through space that could take you to your destination almost instantly? This is the idea behind wormholes, hypothetical passages through space-time that could revolutionize our understanding of travel, physics, and even time itself. The concept of wormholes originates from Einstein's general theory of relativity, which describes how gravity affects the fabric of space and time. According to this theory, massive objects like stars and black holes create curves in space-time. But under certain extreme conditions, space-time might fold in such a way that two distant points connect, forming a shortcut known as an Einstein-Rosen bridge, or what we commonly call a wormhole. A useful analogy is to imagine the universe as a two-dimensional sheet of paper. Normally, to move from one point to another, you have to travel across the surface. But if you fold the paper so that the 2 points touch, you could simply step from one to the other. That's essentially what a wormhole does. It bends the geometry of space-time to allow near-instantaneous travel between two locations that would otherwise be light years apart. But here's the catch. While the mathematics behind wormholes is solid, we have never observed one in nature. They remain entirely theoretical. One of the biggest problems is stability. A natural wormhole would collapse almost instantly under the force of its own gravity. Scientists theorize that a special type of material known as exotic matter might be able to keep a wormhole open. But so far we have no concrete evidence that exotic matter even exists in the amounts needed. So, are wormholes real? Could they be lurking somewhere in deep space? Or are they simply a fascinating byproduct of theoretical physics? In the next chapter we'll explore the different types of wormholes and what they might mean for space travel. Wormholes come in different theoretical varieties, each with unique properties and challenges. While none have been observed, physicists have categorized them based on their structure and potential behavior. Let's explore the main types. First, we have the Einstein-Rosen bridge, proposed by Albert Einstein and Nathan Rosen in 1935. This type of wormhole is mathematically derived from general relativity, and is often associated with black holes. It suggests that a black hole could be connected to a white hole, a hypothetical opposite that spews out matter instead of consuming it. However, Einstein-Rosen bridges are thought to be incredibly unstable. The moment anything enters, the tunnel collapses, making it useless for travel. A more interesting concept is the traversable wormhole, which could theoretically allow matter, even spacecraft, to pass through safely. Unlike Einstein-Rosen bridges, these would require a special ingredient: exotic matter. Exotic matter isn't just any kind of unknown substance, it must have negative energy density, a property that could counteract the gravitational forces pulling the wormhole shut. Scientists have observed tiny amounts of negative energy in quantum physics experiments, like the Casimir effect, but not nearly enough to stabilize a wormhole. Another speculative type is the Lorentzian wormhole, sometimes called a time tunnel. This variation suggests that if a wormhole's two ends move at different speeds relative to each other, they could allow for time travel. If one end moves close to the speed of light and the other remains stationary, an object traveling through the wormhole might experience time dilation, meaning it could theoretically arrive at a different point in time. Then there's the quantum foam wormhole, proposed by John Wheeler in the 1950s. According to quantum mechanics, space-time at the smallest scales is constantly fluctuating, possibly creating microscopic, short-lived wormholes. While too small for travel, some theories suggest that these quantum-scale wormholes could be scaled up or manipulated in ways we don't yet understand. If any of these wormholes exist, they could provide shortcuts across space or even time. But how could we create or detect one? In the next chapter, we'll explore the potential mechanisms for building and stabilizing a wormhole. So could wormholes actually exist? Some physicists believe they might naturally form within the extreme environments of black holes or the early universe. Others propose that if we find enough exotic matter, we could artificially create one. In 2017, a theory called the ER=EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggested that wormholes might be linked to quantum entanglement. This raises the possibility that wormholes are more than just a mathematical curiosity, they could be fundamental to the way our universe works. Currently, no direct evidence of wormholes has been observed. However, some astrophysicists believe that anomalies in gravitational lensing, where light bends around massive objects, could be signs of hidden wormholes. Another possibility: advanced civilizations. If intelligent extraterrestrials have mastered the technology to stabilize wormholes, they could already be using them for interstellar travel. If we ever detect an artificial, stable wormhole in space, it might not be natural at all. Wormholes might seem like a science fiction dream, but serious scientific challenges stand between us and their potential use. Even if they exist, harnessing them for travel, or even proving their existence, poses nearly insurmountable obstacles. 1. Stability, the great collapse problem. One of the biggest challenges in wormhole physics is their inherent instability. Einstein's equations suggest that if wormholes do exist, they would collapse almost instantly. The walls of a wormhole would snap shut faster than light, making it impossible for any object, even photons, to pass through. To prevent this, scientists theorize that exotic matter with negative energy density could counteract the gravitational collapse. This exotic matter isn't ordinary antimatter but a form of energy that behaves oppositely to normal matter, pushing space apart instead of pulling it together. We have observed small amounts of negative energy in quantum vacuum fluctuations, but we don't know if it exists in large enough quantities to stabilize a wormhole. Could we artificially generate exotic matter? Some physicists speculate that harnessing the Casimir effect, where vacuum energy is manipulated between two metal plates, could be a stepping stone toward producing usable amounts of negative energy. But this remains purely speculative. To size and usability, the scale problem. Even if wormholes do exist, they may be microscopic, far too small for a spaceship, let alone a human, to travel through. Quantum mechanics suggests that at the Planck scale, around 10 to the minus 35th meters, the fabric of spacetime is turbulent and constantly fluctuating, creating tiny, short-lived quantum foam wormholes. Some theories suggest we could expand a naturally occurring wormhole. A highly advanced civilization, or future humanity, might find a microscopic wormhole and use some form of advanced energy to enlarge and stabilize it. One speculative method involves using powerful cosmic strings, hypothetical one-dimensional defects in spacetime, to stretch a wormhole. However, this idea is purely theoretical, and cosmic strings themselves remain hypothetical. 3. The paradox of causality, time travel risks. If traversable wormholes allow shortcuts through space, they might also allow travel through time. This raises a massive issue: causality violations. Imagine someone travels through a wormhole and arrives in the past before they left. This could lead to paradoxes like the famous grandfather paradox, where someone could theoretically prevent their own existence. Physicist Kip Thorne, who consulted on the movie Interstellar, explored the idea that quantum effects might prevent such paradoxes. The Novikov self-consistency principle suggests that time-traveling events must be self-consistent, meaning you could interact with the past, but only in ways that ensure history remains unchanged. However, this is purely theoretical. If wormholes allowed time loops, they could violate fundamental laws of physics, like the second law of thermodynamics, which states that entropy must always increase. Some scientists believe that quantum effects or unknown physical principles might prevent such paradoxes from occurring. 4. Can we detect wormholes? Even if we can't use wormholes yet, how would we know if they exist? Scientists have proposed several methods. Gravitational lensing anomalies. Wormholes could bend light in strange ways. Unlike a black hole which absorbs light, a wormhole might create a double image of distant stars as light bends around its two mouths. If we observe unexplained distortions in distant galaxies, they could hint at hidden wormholes. Exotic particle traces. Some theories suggest that high-energy cosmic rays or strange fluctuations in space could indicate the presence of a wormhole. Simulations and quantum experiments. Some researchers are testing quantum mechanics at tiny scales to see if baby wormholes might exist in particle interactions. 5. The future of wormhole research. So, will we ever create or find a wormhole? Right now, no known technology can generate or stabilize one, and wormholes remain a theoretical concept. But that doesn't mean they are impossible. The coming decades of research in quantum gravity, string theory, and black hole physics may uncover clues. Some scientists believe that if we ever develop a theory of quantum gravity, uniting Einstein's relativity with quantum mechanics, we might discover that wormholes naturally form in extreme environments, like the hearts of black holes. For now, wormholes remain a tantalizing mystery. They represent a possibility, not just for faster-than-light travel but for reshaping our understanding of the universe itself. The question isn't just whether they exist, but whether we can ever use them. Could the key to unlocking the cosmos lie in these hidden tunnels of space-time? The search continues. Wormholes remain one of the greatest mysteries in modern physics. They challenge our understanding of space, time, and reality itself. While we have no proof they exist, the math behind them is sound, and the possibilities they present are too exciting to ignore. If humanity ever learns to harness wormholes, we could explore the universe in an instant. Until then, we'll keep searching, theorizing, and dreaming about what lies beyond the cosmic tunnels of space-time.